Welcome back, everyone. In this video, I will begin going over the lecture for the chain rule. Now, the chain rule, this is usually thought of as kind of the big rule of derivatives. And the reason it is most of the derivatives we've been doing before, they all had something in common, which is not always going to be true when you're dealing with derivatives of many functions that occur in nature. So if you're thinking about being a major or doing something related to physics or engineering or even math and even biology, most of the functions we dealt with, in fact, all of the functions we dealt with, all the derivative rules involve just x. And that's not going to be the case in naturally occurring things. So what I mean by that is, think about the specific rules. I'm not talking about the product rule or the quotient rule, where it tells us how to add, multiply, or divide and do the derivative of those, not the addition ones, but I mean more so the power rule. So d over dx, we know how to do the derivative of x to the n power, but it's just x to the n power. It's not something with x to the n power. And then also the derivative of just x, we know how to do. We know how to do the derivative of very specifically e to the x. Now there's kind of two things that working here. We know how to do the derivative of e to the x specifically. We don't know how to do the derivative of any other number to the x power. And we also don't know how to do the derivative of e to anything besides just x. And then the same thing goes for all 6 trig functions. I'll just write down sine. We know the derivative with respect to x of sine of x, but also the other 5 as well. But the point here is that we only know how to do it if the variable we are taking the derivative with respect to, which is x, that's what this means. That's why we've been saying it from the beginning and writing it down every time when we do the derivative. It matches the thing, the variable inside. So if I had 2x, if I want to do this derivative of sine of 2x, this rule doesn't work. If I want to do the derivative of e to the 2x, e to the x plus 1, e to the anything except x. I could even do the derivative of e to the sine x. I just can't do that yet because we only have a rule for just x. So what the chain rule is going to do is it's going to let you do any combination like that. If I want to do the derivative of e to the x squared plus cosine x, I could just have the messiest exponent I want to have, and the derivative from the chain rule will be able to be done. All right, and I wanted to write down just a couple of quick examples of things that, naturally don't occur like this. Anything that deals with like exponential growth or decay has something called a growth or decay constant. You don't have to be very familiar with it, but it's typically seen in biology or chemistry where you have exponential growth or decay. And those functions usually look something like this. You have y equals a number, we'll say p times e to the RT power. You may be familiar with the PERT formula, where in this example, t would be our variable. Well, we couldn't use our derivative rule up here for e to the x, or for thinking about it this way, e to the t, because of the r there. We need the chain rule to be able to know how to do the derivative of this. Another example is if you think about your generic graphs of trig functions. If you remember these, it's something like y equals a, and then I'll just do for sine, and then we do inside the sine we have b parentheses x minus c plus d. The inside of the sine is not just x, and if it's not just x, we can't use this rule like I described. So the chain rule is going to allow us to do many of the rules or many of the derivatives that we were not able to do already. And these are just 2 examples. There are tons of other types of examples of things that occur naturally when you model their formulas, that it's not just x, or if you have t for time, it's not just t. All right, so I want to go ahead and start. The chain rule is going to tell you how to do the derivative with function composition. It says let f and g be differentiable functions. Then the derivative f of g, remember that, hopefully you remember that function composition notation. We have f circle g, it's written f of g. Sometimes you can write it f parentheses g, but that looks a little confusing, so not often would you write it like that. but it's given by the derivative of f of g of x equals, and like I said, the parentheses here, so f of g of x is the same thing as f circle g of x. It is given by the formula f prime of g of x times g prime of x. Now, one thing to remember when you're looking at this formula and how we're going to actually read it, because like with all the other derivative rules, it's better to remember how to read it. You should have the formula somewhere in the back of your head, but reading it is the most important thing. The above notation, when you're talking about function composition, the function that comes to the right, or the one that's closest to the x, which in this example is g, is considered the inside. And the one that's farther away, which is f, is considered the outside function. And if you think of f and g like that, the chain rule says this. It says, this first part says, do the derivative of f, which is the outside. Well, let's go ahead and make sure you write this down, because this is a very, very useful way to think about it. Do the derivative of the outside. Now, what you'll want to notice is when we do the derivative of the outside, what's still inside is exactly g of x. Keep the inside the same. And then in a lot of ways, when you see problems worked, this will feel like just doing your old rule. You'll just have something that's not x. The additional part of the chain rule is you multiply the entire thing, then multiply by the derivative of the inside, g prime of x. All right, so I just wanted to mention that when we go through problems, it's going to look like the part that I've written here in black. The first part is going to look a lot like using one of our old rules. Now, when you talk about the chain rule, you could write down a new rule for every single rule that we've already had before. A new rule for the power rule, a new rule for the derivative of e to the x, and so on. But the main thing is that if you understand what the chain rule is saying, you don't have to think about doubling up on your rules. You could just use your old rules from before and follow the outline here. Now, something I've done a few times throughout the derivative rules is proving them. The chain rule is the hardest one to prove. It's very messy, and also it's not just an algebraic one. It's very complicated. Now, if you wanted to read it, it would probably, take me about 45 minutes to an hour just to do it on here. But if you go to this website and you can write it down, derivative proofs, they have a lot of derivative proofs in here, not all of them. But the chain rule is, the chain rule is proven for you. And I just wanted to skim through real quick. I'm not going to read in the details, but you can see that it starts off by doing the limit definition of the derivative like they all do. And then really the hard thing about the chain rule and proving it is that you redefine stuff. And that's not typically a natural thing. So you have to redefine something, go through, do a lot more steps. Then after you've kind of set it up, done a lot of work just to get there, then you can do the algebra part. And at the end result, you're finally there. All right, but like I said, I don't want to spend time doing that one because with the chain rule, the most important thing is just practicing. And what I'm going to spend the rest of the section on is just practicing using the chain rule. Other things that we've done in the previous sections, like finding velocity and acceleration because the original function is a position function, that still be valid. Finding the equation of tangent lines, still valid, but we don't want to really focus on that in this section. It's just very, very important that you see many examples of the chain rule done. And that's what we'll be doing for the rest of the section. All right, so go ahead and jump in. What I'm going to do, I'm going to leave the wording in here just for the first couple examples and then show you how to relate it. Relate this wording, do the derivatives with all our old rules and everything else. All right, so this one, it says find f prime of theta if f of theta is cosine of theta squared plus 4 pi theta. Now the point here is that before we could only do the derivative if the entire inside of the cosine is theta. And we know the derivative of cosine of theta would be sine of theta. Well, the chain rule is going to tell us how to figure out the rest. Right. Now, the most important thing is really to be able to locate the outside and the inside. And I think with trig functions, they might be the easiest ones because the trig function is very literally written on the outside. So cosine, the outside function, is cosine. Technically, it's cosine of theta, so you don't really just write cosine, or you never really write a trig function without an angle. But if it helps you just to write the cosine because there's not really a theta attached there, don't write it. Just do whatever's going to help you get through the problem the easiest. And then the inside is where the angle goes. But the inside the entire parentheses is this theta squared plus 4 pi theta. Now, if you don't remember a lot about function composition, the real reason you need a theta here, if you want to be very formal about it, I'm just going to do it for this first one, is that when you do function composition, when you put the outside and then the inside like this, really what you do with the inside is you plug it in to theta for the outside function. So when you plug in this, you would get cosine, and then in place of theta, you put the entire theta squared plus 4 pi theta. And that's why we really need that theta written there if we're going to just specifically write down the outside function. Okay, so how are we going to use the chain rule in this example? Well, maybe the best thing to do is just start by realizing if you read the chain rule in words, you have to do the derivative of the outside. We have to keep the inside the same, but we already know what the inside is. So let's keep a record of that. We know what the inside is. And then we need to multiply by the derivative of the inside. Well, maybe it's a good idea just to write down what is the derivative of the outside and the derivative of the inside, because we're going to need them both. So let's go ahead and do that. Derivative of the outside. Our outside function is cosine of theta. What's the derivative of cosine of theta? That's something we know because it's just theta. And you get negative sine of theta. What's the derivative of the inside? Well, the derivative of the inside with respect to theta, the derivative of theta squared is 2 theta, plus the derivative of 4 pi times theta. 4 pi is a number, which just stays there, and the derivative of theta is 1. We get 4 pi. All right, now how can we use this? What does the chain rule say to do? The chain rule says do the derivative of the outside. So f prime of theta, the first thing we have is the derivative of the outside, but I'm going to not write the theta in. Why am I not going to write the theta in? Because keep the inside the same. So the inside of the negative sine of theta, I don't really use sine of theta. I don't really use theta. I still have to keep my inside in there, the original inside, the theta squared plus 4 pi theta. That's what this is saying here. I do the derivative of the outside, the derivative of cosine is negative sine, and then I leave the inside theta squared plus 4 pi theta the same. All right, and this is kind of what I was talking about before when I was describing, is that when you do the first part of the chain rule like this, it looks a lot like our old derivative rule. You have the derivative cosine is negative sine, and you're just kind of leaving the inside alone. It's exactly said that in words. But the chain rule part, at least what I think about being the chain rule part, is this part. You multiply by the derivative of the inside. The derivative of the inside we figured out. And I'm going to put in parentheses because there's an addition there. 2 theta plus 4 pi. Right? Now, once you're here, you've actually you're done. What we have not done, I guess you could simplify it by putting the 2 theta plus 4 pi in front, just because typically if we're multiplying things, we like to put the trig functions in the back, but you don't really have to do that. It's up to you if you want to rearrange it. I'll go ahead and rearrange it. So we have the negative sign here. I'm going to put the 2 theta plus 4 pi in front. Now keep in mind, the only thing inside of this sign is this. So this is on the outside of sign, and I can move it as I need to. And then times sine, but the theta squared plus 4 pi theta is inside the sign. So that's all one piece together. All right. But one thing I wanted to go ahead and do again, especially with this first example, is kind of point out what we did. Compare f of theta to our derivative before we simplified. What did we do first? We did the derivative of the outside. What's the derivative of cosine? Negative sine. Okay, so that's like this part here. We did the derivative of the outside. Now what's the next part? The next part of our answer was the inside, and we kept it the same. So the next part's the inside, and that's exactly what this says in words. We kept the inside the same. So the first two steps, we did the derivative of the outside, derivative of cosine's negative sine. We kept the inside the same, and then we multiplied by the derivative of the outside. And we figured that out below here. The derivative of the outside was 2 theta plus 4 pi. The reason why I want to point that out is when you're doing the chain rule, while it's nice to really, kind of keep track of these things, you're going to pretty much want to do it in line. It's sort of like with the power rule, not the power rule, the product rule and quotient rule. We do the derivative of the first times the second, the derivative of the second times the first, and with the product rule, we add them. Well, we didn't really write on the side, what's the derivative of the first? What's the derivative of the second? We wrote it in line. So I'm going to do that with the next one. I'm going to write it in line because this will keep your work less cluttered. When these functions get more complicated, you could have the chain rule interacting with the power rule, not the power rule. It can interact with the power rule as we did here, but it can interact with the product and quotient rule. It can get messy. So doing it in line is more useful. All right, so the first thing, we want to find w prime of x if w of x equals 3x to the fifth plus 5 e to the x to the third power. Why do we need the chain rule here? Well, we need the chain rule because we're raising something that's not just x to the third power, right? We have this entire thing being raised to the third power. It's very easy to look at this and say, well, I know how to do the derivative of 3x to the fifth. I know how to do the derivative of 5e to the x. And that's good. You should know how to do them. But it's not by itself. Because we're raising to a power on the outside, we have to use the chain rule. So let's go ahead and write that down. We're raising to the power on the outside, which means we're going to use the chain rule. And it's really your job. Probably the hardest thing about learning the chain rule is identifying what's the inside, what's the outside. Well, usually when you're dealing with the chain rule, the inside is the easiest thing to see. The inside is exactly what I have underlined here because it's the part being raised to the third power. The inside is 3x to the fifth plus 5e to the x. Now, what is the outside? The outside is, honestly, it's best thought of as what would happen if you replace the inside with just x, since our variable is x here. If you replace the entire inside with x, what do we get? Well, all this would be x to the third power. So our outside function is x cubed. And really what I'm looking at here is the cubing part. That's my outside thing. I'm doing something and I'm cubing it. So that is my outside function. Right. When it's not a trig function or an exponential function, you don't have the x or something written there. You just have the power to go by. So it can be a little more confusing to look at. But let's go ahead and see, how do we write this in line? Well, w prime of x, we do the derivative of the outside. What is the derivative of x cubed? Well, it's the derivative of x cubed is 3x squared. But the way I'm thinking about this power is I'm just doing the power rule pretending this is x. I'm doing the power rule pretending the inside is x. And if it helps, maybe just cover it on your screen. I'll kind of scratch through it, but I'm going to erase this. Imagine this was just x. Don't worry, I'll erase that so we can look at it in a second. If I was doing the derivative of x cubed, I would have 3x squared. But instead of having x, because that's not really what the inside is, I'm going to go ahead and erase that. And this is the derivative of the outside part. And I want to leave the inside, the 3x to the fifth plus 5 e to the x inside. Right? And once again, maybe pause it, rewind the video if that's not sticking, and watch it again. Hopefully with the amount of practice examples we have in this section, it'll start to come to you. All right, now what do we do on the side here? Because that's really the first part. Do the derivative of the outside, keep the inside the same. Now we multiply by the derivative of the inside. And this is what I mean by inline. It's up to you whether you want to do the derivative of the inside and just write it down. That's fine. What I like to do is I like to do the derivative of the inside very literally. So d over dx of the inside, 3x to the 5th plus 5e to the x. All right, so in that sense, it sort of looks like when we would do the product rule or the quotient rule, or when we started at the very beginning of doing derivatives, is we would write the indicated derivatives and then we would do them. We got 3 parentheses 3x to the 5th plus 5e to the x squared. And then what's the derivative of 3x to the 5th plus 5e to the x? Well, neither of these require the chain rule at all. It's just x to a power and e to the x. We already know rules for that. We do the power rule on the first one. We get 15x to the 4th. 5 times 3 is 15 plus, and the derivative e to the x is itself, we get just 5e to the x. Right? And this is our derivative. Now you can simplify a little bit, but literally the only thing I can see to do is factor a 5 out of the second part here. And you would get the 5 coming all the way out front to make 15. But since it's just a number and it's not a weird number, I'm just going to leave it like this. But once again, I highly encourage you to get these first two examples down. There's many more in this section, which we'll go through and I'll pick up in a new video. But if you're not seeing, maybe go back and watch the first example now that you've seen another example. Maybe it'll help if you weren't fully understanding how I did the first one. But you really want to try to get these first two down because the chain rule, this is honestly about as basic as we can do the chain rule because it's just the chain rule with the power rule or e to the x, just the basic examples. So make sure you get these down, and then when you do, I'll see you in the next video.